Swayam Prabha. Digital India. Educated India.
Welcome back to the course Mechanics of Solids. So, in the last lecture we were solving one numerical problem to understand the moment curvature relation, and there we have seen that we established four different we established the differential equations, and from there we got four integration constants, and we established two boundary conditions, two continuity conditions by which we could find out the magnitude of all unknown integration constants. So, those things already we have done in the last lecture, and this was the problem was taken. So, our objective is to find out the deflection at point D, okay, the point where the concentrated force is acting. Okay. So, now from equation 6, if you do this operation equation 6 into 1 minus equation 7 into A, if you do this operation, then you will be getting simply C4 equal to W A cube by 6. Then from equation 5 you will get C3 equal to, so I am not writing all the steps, you can find out that thing by your own, okay, W A by 3L L square plus A square by 2. Okay. And then finally, you will get from equation 7, you will get C1 equal to W A by 2 minus L by 3 minus A square by 6 L. Okay. So, you have got all the integration constants C1, C2 is already 0, already we have seen in the last lecture that C2 was 0, then C3 and C4. So, all the integration constants have been obtained. Now, we will be considering one special case or the special situation when D is at the midpoint of the beam. Okay. That means, say some special condition we are considering, putting A equal to B equal to L by 2, and in the bending equation. Okay. So, in the moment curvature relation your x is equal to L by 2. That means, section 1 is valid from 0 to L by 2 and section 2 is valid from L by 2 to L. Okay. So, if I put that, so from our earlier equation whatever we have derived for section 1 I can write W B from section 1 I had that equation like this, W B x cube by 6 L plus C 1 x, if you recall, right, C 2 was 0. Okay. So, from this I can simply write by putting x equal to L by 2 in this equation, okay, I can get E I V equal to W L cube by 48, of course minus. Okay. Therefore, V at x equal to L by 2 is equal to minus W L cube by 48. So, minus sign is for V is downward, that means y is upward, V, that is the deflection, is downward due to the application of the load, that is why it is the minus sign is coming. And so, what does it mean? That means the central displacement of the, or the deflection of the beam under this load W, when A equal to B equal to L by 2, at that time that deflection will be coming as W L cube by 48 EI. So, here you can see as your W increases, your deflection also will increase. As your length increases, the deflection will be increased in the cubic term, okay, in the cubic power, and EI, that is the flexural rigidity, if it increases, then your deflection will be getting reduced. So, that is why this is nothing but your it is a measure of rigidity, that means how rigid the beam is. Okay. So, anyway, so whatever I wanted to say, that by establishing or by using your moment curvature relation, you have got the deflection, okay, at the midpoint of the beam like this. Similarly, at any point, because you know all the integration constants, at any point you can find out the deflection of the beam, okay, by using the proper equation and the boundary conditions. Okay. So, now we can find out the slope also. We can find out the slope at x equal to 0, okay, your EI dV dx equal to C1, okay. At x equal to 0 means at point A you want to find out the slope. Slope is nothing but dV dx, and if you recall your section 1.1 equation valid for section 1.1, from there I can get simply EI dV dx equal to C1. So, from there I can, putting A equal to B equal to L, I can simply get minus W L square by 16. So, therefore, I can write that slope at x equal to 0, okay, is equal to minus W L square by 16 EI. That is the slope, okay. That is the slope of your deflected curve, okay. Similarly, you can find out dV dx at x equal to L, dV dx at x equal to L by 2, at any point you can find out your slope by using the proper equation, okay. I hope you have understood this, okay. Now, this is one workout example, okay, for understanding the moment curvature relation and how to find out the deflection, okay, at a particular point in the cylinder member under the action of some bending moment. Now, we will see later on some energy method, okay. By using this energy, using that energy method, very simply you will get this kind of, or you can solve this kind of problem, okay, the deflection problem or the slope problem. So, that will be discussed later on, but at this moment we are trying to find out the deflection from our moment curvature relation, and because you are, for getting your V, you are doing you are performing integration twice, right. So, that is why sometimes in some books it is also known as double integration method, okay. So, nevertheless, so this is the problem based on your moment curvature relation. Now, we will look at the method of superposition which is valid for our system also. Now, let us see what is that. So, as you have seen that by using the moment curvature relation, the problem, though the problem was very simple, but it was little bit say lengthy, right, not complicated, I would not say complicated, but it is little bit lengthy. So, that is why people, if you know the solution for some known loading conditions, if you know the solution means slope as well as the deflection, maximum deflection for some known structure or the known loading condition, then you can superimpose that thing to get the deflection or the slope for a complicated system. So, that is the idea of method of superposition, okay. Now, what does it mean? The method of superposition is valid for the linearly elastic system, which exactly we are talking of in this particular course. So, it means along that we are writing 1 by rho, okay, 1 by rho, as you know, that is d phi ds. Okay, and along the y axis we are plotting mb. So, now what we are doing, so this is your linear elastic system. So, if you apply an incremental bending moment delta mb, for that you will be getting some incremental change in 1 by rho. Similarly, in the next increment, if you increase, there also you will be getting some incremental change in 1 by rho. Now, the idea is that the total, let the total bending moment be the sum of a number of contribution due to separate loading. That means, suppose I have, this is one slender member under the action of different loads, okay, 1, 2, 3 and 4. There are different loads are acting on this slender member. Now, this is equivalent to, say, this is the same beam with this load plus this is the same beam with this load, this is 1, this is 2 and so on. Okay. So, if you add them together, you will be getting the same effect. Okay. So, if you find out the bending moment for this whole beam at a time, or if you find out the bending moment of each individual beam and then you, if you add them together, sum them together, you will be getting the same magnitude of the bending moment at a particular section. That is the idea, and that is known as method of superposition. Okay. So, that let the total bending moment be the sum of a number of contribution due to separate loading, as I was telling you. Then I can simply write mb, that is the total bending moment, is equal to mb1 plus mb2 plus so on up to n number of beams. Okay. So, now let V1, V2 be separate deflections such that your EI d2 V1 dx2 is equal to mb1. Fine. Okay. If V1 is caused due to the bending moment mb1, so this is the moment curvature relationship for bending moment mb1 and V1. Similarly, your EI d2 V2 dx2 is equal to mb2. Finally, I can write then the sum V equal to V1 plus V2 plus so on. That means, the deflection in the actual beam, okay, is equal to the deflection of each individual beam. I mean that is a summation of all the deflection together will give you the total deflection, right, as per the method of superposition. Okay. So, this is nothing but EI, I can write EI d2V dx2, right. This is the, I am going to establish the moment curvature relation for the original beam where all the loads are there, is equal to, I can separate it like this because EI is constant. Okay. So, EI d2 dx2, in place of V I can write V1 plus V2 so on. Okay. So, from this I can write EI d2 v1 dx2 plus ei d2 v2 dx2 so on. Now, what is this? This is nothing but MB1, this is MB2 and so on. And what is this? This is nothing but your total bending moment in the horizontal beam, and that is equal to the summation of all the individual bending moment, okay, caused by individual loading system, as I was showing in the figure, right, load 1, 2, 3, 4. Similarly, you can find out that. So, this is nothing but your method of superposition. Okay. So, now what I mean, how it will help me? Okay, let us see that. Okay, how it will. So, suppose this is one cantilever beam, there is a load concentrated force applied here, the total length of the beam say L, and there is one concentrated moment applied at the free end. I want to find out the deflection at the free end, that is my job. Now, you can apply the moment curvature relationship in the actual beam or the original beam, and then you can find out by taking two sections and whatever you have seen in the last numerical problem. In that way you can proceed. So, that will be a little bit say lengthy process. Okay. I should not say complicated, but lengthy process. So, what we will do here, okay, intelligently, will separate the loading system. That means, this is equal to, this system is equivalent to two systems. One system is this, where only the concentrated force is acting, and another system where only the concentrated moment is acting. I have separated two systems. Now, if I add these two things together, I will be getting the original system. That is your method of superposition. Now, here in the deflected shape, so under this loading, the deflected shape, probably deflected shape will be like this. So, this is your say delta 1, okay. That means the deflection at the free end due to the application of the concentrated force P at this point, and this moment will try to deflect the beam like that, and this is say delta 2. Okay. So, your actual or the resultant deflection, okay, under the action of both the things together is nothing but say delta, which is nothing but delta 1 minus delta 2. Agreed? Just algebraic summation. Now, if I consider this is one basic system and this is another basic system, and if I know the solution, of course, by following the same process like your moment curvature relationship, if we know, if I have a cantilever beam, if I have a load concentrated force on the cantilever beam like this, the delta 1 value if I know priori, okay, I mean beforehand, if I know this delta 1 value, and if I know the delta 2 value under this kind of situation beforehand, then I just put this thing here to get the resultant delta which is applicable for this system. Understood? So, this is the say intelligent way, okay, by which you can solve different complicated systems. Okay. You separate them for different systems, and then you go to the basic system, and those basic system solution should be known to you prior hand, okay, and then based on that you can find out the resultant deflection. Similarly, okay, so let's see some basic systems. So, these are some basic systems. Okay, as you see, these are some basic systems. This is some system 1. Okay, as this problem is given. So, if P is applied here, so you can find out delta max phi max at the free end. So, that value is given already. Okay. Similarly, if you have the system like this is your delta max, this is your phi max, which will be happening at the free end. Similarly, this is your third system, fourth system, fifth system, sixth system. So, all these systems, okay, all these systems, if you consider the basic system and if you try to separate or try to make your complicated system, or if you try to separate your complicated system or the original complicated system into different basic systems, and then if you try to obtain the magnitude of the deflection or the slope, and then finally you will get the resultant thing for the original complicated system. So, that is the idea of your method of superposition. Okay. So, now this method of superposition can be used for indeterminate structure also. Okay. Let us see how we can use that. Suppose you have both ends are fixed. So, this is obviously your indeterminate structure. Why? Because here you will be having two unknowns, because I do not consider any axial force. Here you have two unknowns, one vertical reaction and another moment. Here also you have two unknowns, one vertical reaction and one moment, right. So, you have four unknowns, but you have only two equations, right. I mean three equations, right. So, basically you cannot solve it. So, this is your indeterminate structure as whatever we have discussed previously. Okay. So, now this on this beam I am applying some load P. So, this is say A distance, this is your B distance, and then total length of the beam say L. Okay. So, for this system one thing is known to me, because these are two fixed support. So, here your slope will be 0. Do you remember? Here your slope will be 0, because moment is there, right. You have the moment reaction. So, the slope must be 0 at these two ends, end A and end B, C. Okay. So, this is your A and this is your C, and this point say B. So, this can be separated in three basic systems. First one is when you have only the cantilever beam, where you have the concentrated force acting at this point B. This is one basic system. So, this will be deflected this much. So, this is my say delta 1, and this is your say slope phi 1. Okay. Similarly, next basic system will be another cantilever beam. Okay. So, I will be having the vertical reaction, upward vertical reaction. So, that is say R C. Under this action the deflected shape will be like this. So, this is my say delta 2, and this is the angle phi 2, plus what else is left out? The moment reaction. So, for that another basic system I am considering. For that say M C is acting here, and your deflected shape is like this. So, this is your say delta 3, and this angle say phi 3, that is the slope. So, therefore, your resultant deflection. So, now these three are all your basic systems. Now, these basic system solution are known to you. Now, you get the delta 1, delta 2, delta 3 value from the basic systems, and phi 1, phi 2, phi 3 all are from basic systems. And then basically your, if you look at the deflection at point C, deflection at point C is nothing but delta 1 minus delta 2, okay, plus delta 3, okay. And what is the magnitude, actual magnitude as per the boundary condition? What is the magnitude of your delta C? That is a fixed support. There is no displacement or the deflection at point C, that must be 0. Similarly, phi 1 minus phi 2 plus phi 3, that is the resultant slope at point C, that also must be 0 because that is a fixed support. Now, from these two equations you get two unknowns RC and MC. They are not known to you. So, in that process, actually in this method of superposition process, you can even find out the unknown reactions, because this RC and MC are not known to you, because this is the indeterminate structure. They can be found out by solving in this fashion. Okay. So, I will stop here today. In the next lecture, we will be continuing with the discussion regarding this. Thank you very much.